In this video, we will go over proof techniques. We have this summary slide here, so we'll go over inductive reasoning, deductive reasoning, proofs, the contrapositive, converse, and inverse, proof with quantifiers, proof by contradiction, and proof by cases. There are numerous examples, and at the very end, there's like 5 example problems for you to try, and then I do have discussion of solutions. The examples are really important. The more examples you do, the better you get, and it does take practice to get good at this. It's not too difficult to listen to me and follow, but it's much harder at times to know how to start, but that comes with practice. We will start by looking at inductive reasoning, which is on the basis of looking at individual cases, we make a general conclusion. So for example, if we have a function g that takes 2 numbers, m and n, then the function is equal to n squared plus n plus m. So when we plug in m is equal to 1 and n is equal to 2, we're going to get 1 squared plus 1 plus 2, which is 2 squared. When we plug in 2 and 3, we'll get 3 squared. And when we plug in 5 and 6, we get 6 squared. What we might guess using inductive reasoning, in other words, by looking at this case, is we might take the guess that for all n, that g, when we plug in n and then n plus 1, is equal to n plus 1 squared. And we can actually prove this using algebra. So if we look at g of n plus 1, we have our n squared plus our n plus 1. And then we do some algebra and we'll see that's equal to n plus 1 squared. And this is in contrast to deductive reasoning, where we apply a general principle to a particular case. So for example, if we said gn in general for n and n plus 1 is equal to n plus 1 squared, then we can deduce, using deductive reasoning, that g of 124 and 125 is going to be equal to 125 squared. Our first example is the question, in what ways was deductive reasoning used to prove gn n plus 1 is equal to n plus 1 squared? Recall the proof was written here, but I have it in a 2-column proof where we have the steps on the left-hand side, and on the right-hand side we have the justification. So we start with gn n plus 1, and we use the definition of it. That's going to be n squared n, and then our n plus 1. And now we use algebraic properties. So we know these properties are true in general, and we're going to use it for our example in particular. So we're using deductive reasoning. Our next step is also algebraic, so it is deductive, and we have finished our proof. In general, for proofs, we have some set of hypotheses that implies a conclusion. So P implies Q. P is called the hypothesis, Q is called the conclusion. And if you recall, the implication is true unless P is true and Q is false. Thus, to show P implies Q is a tautology, we must show whenever P is true, then also Q is true. And in general, proofs, you can think of it as building a bridge or a connection from P to Q using definitions, assumptions, axioms, theorems that have been previously proven, logical equivalents, and statements that are logically implied from the previous statements. We will do some examples of this proof, and I'll show you what I like to do to highlight this bridge or connection. But before that, we'll have one other set of topics, which is contrapositive, converse, and inverse. If we have the implication P implies Q, the contrapositive is not Q implies not P. And these two, the contrapositive and the original implication, are logically equivalent. So in other words, if P implies Q is true, then not Q implies not P is true. The contrapositive is logically equivalent to the original. And that is significant because if you need to prove P implies Q, you can also prove not Q implies not P, and therefore P implies Q. We also have the converse, which is Q implies P, and the inverse, which is not P implies not Q. The converse and inverse are logically equivalent to each other, but they are not logically equivalent to P implies Q. It is a very common mistake for people to argue the converse or to prove the converse when they try to prove P implies Q, but they are not logically equivalent. So you cannot argue the converse to do this proof. You can argue the contrapositive though. We will start with what is the contrapositive if 17 is odd, then M is an odd number. And then we're going to construct the proof. I have copied the statement here. If 7M is odd, then M is an odd number. So I've identified my P and I've identified my Q. So my statement here is equivalent to P implies Q. To get the contrapositive, I want not Q implies not P. So not Q is M is not odd or M is even, implies, and then not P would be 7M is not odd or 7M is even. So this here is the contrapositive statement. If M is even, then 17M is even. And because the contrapositive is logically equivalent to the original implication, to prove that 17 is odd, then M is an odd number, we can prove the contrapositive. So I'm going to use this idea of building a bridge, and I'm going to build it from the hypothesis, if M is even, and then I want to show Q, the conclusion. So if M is even, I'm going to start with given M is equal to 2k for some integer k. That's another way of saying that M is even. And then to show my bridge or my connection, I like to say what it is that I need to show in my proof. So my goal is to show that 17M is also even. In other words, 17M is equal to 2j for some integer j. So here is my guidance, and I'm going to start with my given. M is equal to 2k for some integer k. And this is given because M is an even integer. And now I will consider 17M. Well, that's equal to 17 2k. So I'm just plugging in 2k for M here. And I have my justification since M is equal to 2k. Next, I have my associative law multiplication, so I can move the k over next to the 17. And then my 17k is just another integer, which I will call j. So now I've shown that 17m is of the form 2j. In other words, 17m is an even number. And actually this proof here, or proving the contrapositive, is actually easier than proving the the original implication. The next example, write the converse if m squared is greater than 0, then m is greater than 0, and then we want to evaluate the truth of the original statement and of the converse. And note, I'm not asked to prove either of these, but just evaluate if the original statement and the converse are true. I've rewritten my original statement here. If m squared is greater than 0, then m is greater than 0, and I've identified my p and my q in my implication p implies q. To do the converse, I need q implies p. So here's my q. If m is greater than 0, then p. M squared is greater than 0. The original statement is false because, for example, if m is equal to negative 2 squared is greater than 0, but m itself is less than 0. However, the converse is true. So here, because the original implication is false, but the converse is true, you have an example where you can see the converse is not logically equivalent to the original implication. The next example is to write the contrapositive, just in practice, write the contrapositive and converse of each statement. The first, you can work here only if you have a college degree. This is probably the trickiest one. The second, the car will not run whenever you are out of gas. And the last is continuity is a necessary condition for differentiability. So why don't you pause the video and give them a try. The first statement is, you can work here only if you have a college degree. And this is the same as saying, if you can work here, then you have a college degree. It is very tempting to think that if you have a college degree, you can work here is equivalent, but it is not. This statement tells you that having a college degree is necessary to work here. However, this statement does not say that it is sufficient. So having a college degree may not be sufficient. That is, maybe there are other requirements to work here. So maybe the requirements are you have a college degree and you have 1 year work experience, which implies if you work here, you have a college degree. And you also have 1 year work experience. So it implies that you have both of these. So that's what it means by it's necessary, but it may not be sufficient. In other words, there may be other requirements. Here I have identified, with my implication, I have identified P, you can work here, and Q, you have a college degree. So to do my contrapositive, I want not Q implies not P. So if you do not have a college degree, then you cannot work here. The converse is Q implies P. If you have a college degree, then you can work here. And the inverse, not P, implies not Q. If you cannot work here, then you do not have a college degree. The next one, the car will not run when you are out of gas. In other words, if you are out of gas, the car will not run. That's P, you are out of gas, implies Q. The car will not run. So the contrapositive, not Q implies not P. If your car runs, then your car is not out of gas. The converse, Q implies P. If your car will not run, then you are out of gas. And the inverse, not P, implies not Q. If your car has gas, then your car will run. Last is continuity is a necessary condition for differentiability. So the implication is if differentiable, then it's continuous. So differentiable is P, continuous is Q. P implies Q. And I look at this because continuity is necessary for differentiability. It is not the same as if it is continuous, it is differentiable, because it is true that continuity is necessary for differentiability, but it also might be that to be differentiable, you might need two criteria, one of which is continuity, in which case differentiability implies continuous, but continuous is not sufficient for differentiability. It's a lot like our first example with the job and the college degree. And now that we have identified P and Q, we can do our contrapositive, not Q. If a function is not continuous, then it is not differentiable. We can do our converse, Q implies P. If a function is continuous, then it's differentiable. And last, the inverse, not P implies not Q. If a function is not differentiable, then it is not continuous. Our next set of topics is proof with quantifiers, proof by contradiction, and proof by cases. One thing I will say about proof by contradiction, that is not often my first impulse to try a proof by contradiction. Often I try, what I end up doing is I try to prove something more straightforward, and I just can't get it. I just can't get it to work. In which case, in desperation, I try a proof by contradiction. So you might be better at having intuition of when to switch to proof by contradiction, or you might be like me, where you are trying to do a proof the straightforward way and you can't, in which case, if you've tried a couple of things that don't work, at some point you should consider trying a proof by contradiction. The first, proof with quantifiers. Once we have quantifiers in a statement of for all x, p of x, and sometimes the for all x is implied. But for this, our strategy is to let x represent an arbitrary member. So this can represent any member from the set or system under consideration, and then we show that p of x is always true. And if we want to show that this is false for all x, p of x is false, it only takes one counterexample to show that p of x is false. And that's because, if you recall, the negation of a for all is that there exists. So if you want to negate for all x, p of x, all you have to do is show there exists one x such that not p of x. Next, for there exists x, p of x, the strategy is to show at least one member of the set for which p of x is true. Another way of doing proofs is proof by contradiction. So if we wish to conclude a statement about P, we show the negation of P leads to a contradiction. We'll do examples. And then proof by cases. Some proofs naturally divide themselves into consideration of two or more cases. So we will do examples next. Our first example, if the sum of a real number with itself is equal to its square, then the number is 0 or 2. And this is an example of a for all. And actually this one's straightforward and easy enough. You may not think about this, but the for all is implied because we're talking about for any real number or for all real numbers. If the sum of the real number with itself is equal to its square, then we have a conclusion. So that this is the for all. So what we're going to do, so in this statement, the for all x is implied. It's trying to make a statement about all real numbers. So we're going to let x represent a real number, and we haven't put any other qualifications on it except that x is a real number. And then we take this hypothesis, if the sum of a real number with itself is equal to its square, so then we put that one restriction on it, the hypothesis. So we make x, the sum with itself, equal to its square. And what we want to do in our proof is eventually build a bridge until we've shown that x is equal to 0 or 2. And we do this using algebra. We have x squared minus 2x, moving the minus 2x over here equals 0. And through algebra, we have x equals 0 or x is equal to 2. Next, we have disprove the statement for all x, p of x, x squared plus x plus 17 is a prime number. And we're going to use this here. Because we have a for all x, to disprove the statement, all it takes is one counterexample to show that the whole premise is false because of the for all x. So again, if I want to know exactly, and this is really overkill, but if I want to know exactly the opposite of this statement, because I want to disprove the statement, I'm going to say the negation of for all x, x squared plus x plus 17 is prime, which means there exists, and then we negate what's inside, x squared plus x plus 17 is prime, which means there exists an x such that x squared plus x plus 17 is not prime. So it only takes one counterexample. And my counterexample is x equals 17 because p of 17 is 17 squared plus 17, which is divisible by 17. Here is another, for every epsilon greater than 0, there exists a delta such that x is between 1 minus delta and 1 plus delta, and 2x plus 3 is between 5 minus epsilon and 5 plus epsilon. So this is another one with the for all. And actually, this is very common later when you're doing limits, proofs of limits and proofs. So this is a very important example for you to kind of get the strategy. So before we state our strategy, we're just going to say we're given an epsilon, and we want to find a delta that meets these requirements. And our strategy in particular is going to be to look at this part of the equation and solve for x in terms of epsilon. And then we're going to plug that in to the other part of the constraint, 1 minus delta, is less than x, which is less than 1 plus delta. So we again start by solving for x in terms of epsilon. So here's our x and epsilon relation. So we have 5 minus epsilon is less than 2x plus 3 is less than 5 plus epsilon. So we can subtract subtract 3 from everything. So we have 2 minus epsilon is less than 2x is less than 2 plus epsilon. And then we can divide everything by 2. So we have 1 minus epsilon over 2. X is less than 1 plus epsilon over 2. So again, we've solved for x in terms of epsilon. So we've had some sort of constraints now put on x. Now we compare that to the constraint that x is between 1 minus delta and 1 plus delta. And what we can do then is say set delta equal to epsilon over 2. And now, given any epsilon, we have found a delta that satisfies these conditions. And also notice, since epsilon is greater than 0, a delta is also greater than 0. So this is kind of a technique that you kind of want to get used to. If you have, if someone gives you an epsilon, that you can find a delta, and then you have this these constraints, then you're going to solve for x in terms of epsilon, and then you compare that x to how the constraints on delta placed on it. Next is an example of proof by contradiction. Let f be an integratable function. So if f, the integral from 0 to 1 of f of x dx, is not equal to 0, then there exists a point x in the interval 0 to 1 such that f of x is not equal to 0. To prove this implication is difficult, so we are going to try we're going to try both contradiction and contrapositive. I will start with contradiction. So we're given that the function f of x, the integral of f of x from 0 to 1 dx is not equal to 0. And then we're going to assume the opposite of what we want to prove. So this is why we need to learn how to negate the there exists. So we're going to negate the there exists a point x in 0 and 1 such that f of x is not equal to 0. And when we negate the there exists, we get the for all x between 0 and 1, f of x, and then that would be the negation of that, is equal to 0. So this is what we are going to assume. Then what we have from 0 to 1, f of x dx is equal to 0 to 1, and if f of x is equal to 0, we can plug in 0 for f of x, and so our whole integral is equal to 0. But that contradicts our given that the integral does not equal to 0, which means our assumption that over here, for all x between 0 and 1, f of x is equal to 0, must have been wrong. And in particular, that must mean that there exists some x in the interval such that f of x is not equal to 0, and we are done with our proof. And just for comparison, I'm going to do that same proof using the contrapositive. And now that I have my not q, I can write my contrapositive, which is not q, implies not p, and not p was kind of easy to do. That's 0 to 1 f of x dx is equal to 0. To prove my contrapositive, I consider my integral from 0 to 1 f of x dx, and that's equal to 0 because of my hypothesis by my assumption that for all x between 0 and 1, f of x is equal to 0. And that would give us the whole integral is equal to 0. So I've written the proof by contradiction here and the proof by contrapositive here so that we can compare the two. And they're very similar because both of them assume not q, and at the end we want to show not p is true. And so if it seems to you when you do proof by contradiction versus a proof by contrapositive that they seem kind of the same, this is exactly why they seem so similar. Here we have another proof by contradiction. Let x be a real number. If x is greater than 0, then 1 over x is greater than 0. If we do this by contradiction, we're given that x is greater than 0, and we want to assume that 1 over x is less than or equal to 0. So we're going to consider 1 over x is less than or equal to 0. We're going to multiply both sides of this equation by x, and then we get 1 is less than or equal to 0, which is obviously a contradiction. So since we come to a contradiction, that must mean our assumption here was wrong, which means the opposite must be true. 1 over x must be greater than 0. Next, we have an example of proof by cases. So if x is a real number, then x is less than or equal to the absolute value of x. Because this is an absolute value, there are two cases, or two natural cases. One is that x is less than 0, and one is that x is greater than or equal to 0. So when x is less than 0, then the absolute value is always greater than 0 because that's the definition of absolute value, which means the absolute value is greater than 0, which is greater than x, which means the absolute value is greater than x. So this part is true. Case 2 is if x is greater than or equal to 0. So then the absolute value of x is equal to 0 by definition of absolute value, which means in this case, x is greater than or equal to 0, that our statement x is less than or equal to the absolute value of x is still true. So in both cases, the statement ended up being true. Here I have a number of examples for you to try. Pause the video, give them a try, and then I have solutions which I'll give a brief discussion of each. For the first one, for every epsilon greater than 0, there exists delta greater than 0, such that x is between 2 minus delta and 2 plus delta implies that 3x plus 5 is between 11 minus epsilon and 11 plus epsilon. This example is very similar to one we had done previously, one that I said you might want to get used to this because you're going to do stuff like this when you're doing limits later. But the idea is that given an epsilon, we need to find a delta that satisfies this condition. And our strategy was to solve for x in terms of epsilon and then plug that into our requirements for delta, that x into our requirements for delta. So here I have solved for x in terms of epsilon, and then I compared that and looked at my requirements for delta, and I see that delta can equal to epsilon over 3. So given an epsilon, this is the delta that will satisfy these requirements. The next one, there exists a real number x such that for every real number y, we have xy is equal to y. So that's a there exists. So to prove a there exists, you just need to show one solution. So in general, xy is equal to y. If you let x equal to 1, that is always true. Problem number 9, prove there exists an integer such that n squared plus 3 halves n is equal to 1. Is this number unique? So again, to prove the existence, we only have to show one number that satisfies this. So here I did the algebra and n is equal to -2, and yes, this is a unique solution. This one here was a little tricky. Prove the log 2 of 7 is irrational. And note, it would be impossible, or at least I think it'd be tricky, to check there's no p over q that's equal to log 2 over 7. So we're going to do this by contradiction. Often contradiction is what I use when nothing else seems to work. So I'm going to assume that log 2 of 7 is equal to a p over q, a rational expression. And that would imply that 2 raised to the p over q is equal to 7. But since 7 is odd, this is a contradiction. So our assumption here must have been wrong, and log 2 of 7 is irrational. Here, prove or give a counterexample. There does not exist 3 consecutive odd integers, a, b, and c, such that a squared plus b squared is equal to c squared. And there's one remark I'm just going to make really quickly. To express an odd integer, you're going to do something of the form 2k plus 1. That's how you express an odd integer. And a couple of things. One, by Fermat's last theorem, you're not going to have integer solutions. So that's one clue. And two, you could try plugging some things in and see if you can get a counterexample, but you won't. But because this is pretty easy to evaluate and express, I would just algebraically see what I can do with this. So remember A, B, and C are consecutive, and they're all odd. So here I have an expression, and I'm sorry I chose the letter A. I probably should have chosen X. But this is my A here. And then B, since it's consecutive, that's going to be equal to 2A plus 2. And then C, since it's consecutive, that's going to be 2A plus 4. So I did the algebra, and I see my solution is not an integer. So no integer satisfies this condition. And again, you would know this from Fermat's last theorem. Or not his last theorem. Actually, that is his last theorem. Anyway, Fermat's theorem. So prove or give a counterexample for every positive integer n squared plus 3n plus 8 is even. So I plugged in the number 1 just to kind of test it out. I have 1 squared, which is 1. 1 times 3, which is 3. And then 8, and that's 12. So it is even. You can plug in some other numbers. Maybe you'll come up with a counterexample, but actually you won't. You can do this all day, but you won't because it's actually a true statement. So what I did is I looked at this. Why would it be true? Well, the sum of two numbers is even. So 8 is even. So if n squared plus 3n is even, that will make the sum even. So I looked at n squared plus 3n, and that I can factor to n times n plus 3. So I'm thinking this has to be even. Well, there are two cases for n. Either n is odd or n is even. So I'm doing this by cases. And if n is odd, then n plus 3, two odd numbers added together, gives you an even, which would make the product even, and then the sum would be even. So if n is odd, this whole expression is even. Now if n is even, that would make this even, so the product would be even, and then the sum would be even. Either way, if n is odd or n is even, this product is even, and then the sum is even, so the whole expression is even. Here I have considered m squared is odd, then m is odd. What, if anything, is wrong with the following two proofs? So first I just kind of wrote this out. The hypothesis is m squared is odd, that's p. And the conclusion is m is odd, that's q. And so we want to prove p implies q. So our first proof, so-called proof, says suppose m is odd. So we're starting with q. Then it has m written as an odd number, which is 2k plus 1. It goes m squared, and it does this algebra, which is odd. And then they say, therefore, m squared is odd. In other words, that q implies p. Even if this is a true statement, q implies p is the converse of our original implication and is not logically equivalent to the original implication, so it is not a valid proof of our original implication. So again, even if this is a true statement, it's not a valid proof of p implies q. This last one, suppose m is not odd. So that sounds like they're starting with the hypothesis of q. M is not, or not q, sorry. It goes to some argument, m is equal to 2k because it's even, it's not odd. Then you square it, and you get something even. Therefore, m squared is not odd. So that sounds like they're concluding not p. And then they do this funny thing, and m squared odd is not m odd. So what they've proven is not q implies not p, and that is logically equivalent to p implies q. So in other words, once you have this part, m squared is not odd, then it is logically equivalent to p implies q, which is m squared is odd implies q, m is odd. So this is a valid proof because they're using the contrapositive. And that's it for this video. It's a lot to take in. It's easy to follow, but sometimes difficult to start on your own. But with practice, you'll get better. Thank you for watching.